Today we're going to look at graphing linear inequalities. Remember, inequalities are less than, greater than type signs, and absolute value equations and inequalities. Some things to remember from when we graphed inequalities on the number line is that anytime you're using less than or greater than, you want to use a dotted or dashed line, and anytime it's less than or equal to or greater than or equal to, we want to use a solid line because that includes the points actually on the line. Okay, so on this first problem on your note sheet, they want us to graph this inequality, 2x plus 3y is greater than 6. To graph that out, there are some different ways we can do it. One way would be to use that cover-up method that we talked about to get the x and y intercepts. Whenever it's in standard form like this, which our equation is, that's a nice way to do it. So what you can do is cover up the y and solve what's left, 2x. And we got a greater than symbol here. For the purposes of finding x-intercept, we'll just change that to an equals 6. So by solving, dividing by 2, we see that 3. At x equals 3, this is where our line should cross through the x-intercept. If you do the same thing now and cover up the y, or I'm sorry, cover up the x, we can find the y. 3y equals 6. So dividing by 3, we see that the y-intercept is 2. Okay, from there, we have enough points now to graph this line out. Okay, so that's one way to do it. Another way, which we've talked about, is to solve for slope-intercept form. So if you solve this for slope-intercept form, we want to get the y alone. We could do that by subtracting 2x from both sides. That cancels out, so now we got 3y equals negative 2x plus 6. We can't combine the 6 and the negative 2x, those are not like terms. And then we could divide everything by 3 to get rid of the 3. That cancels out, we're left with y. Okay, I'm going to skip over 6 divided by 3, that gives us 2. Now 3 does not go into negative 2, but that's okay, we'll just leave that as a fraction because that would be the slope. There's the equation in slope-intercept form. So if we started at 2, which we've already found out as a point on that line right here, and go down to right 3, down to right 3, we have some points we have on this line. We could also go up to left 3 and get additional points. So those are the points our line should be going through. Now to graph it, we want to decide, should we use a solid or dotted line here? Well, looking at the symbol, greater than, it doesn't have the equals to. We don't want to count the points on the line. So we want to use a dashed or dotted line here to indicate that the points on the line do not work. Okay, so once you have the line, before we were done. But in this case, we have an additional step. We need to know which side of the line makes this true. Above the line or below the line, which one is going to work here? Because some points are going to work, some other points will not. What you want to do in this case is test a point. We're going to test a point out to see which side we should be shading on. The easiest point to test is the origin, 0, 0, because 0 is an easy number to multiply and add with. Okay, now the only time you're not going to be able to use 0, 0 to test is if your line actually goes through that point. Then you need to choose a different point your line does not go through. So let's test out the point 0, 0. If we plug 0 in for both x and y here, our inequality becomes 0 plus 0, which is 0. So we get the inequality 0 is greater than 6. Now we want to see, is that true or is that false? Well, 0 is not greater than 6. That's false, which means this point we were looking at, 0, 0, did not come out to be true. All the points then on that side of the line, anything on this lower left-hand side will not come out true. All our answers then are on the other side. So what we want to do is shade in the side where all our solutions are, which would be everything above this line. Any point we pick in this shaded in yellow region here makes this true. So that's where all the solutions are. So when you're graphing inequalities, you have many answers. They're all in this shaded in area. All right, for tomorrow, I want you to try to do number 2 here. Graph the line Make sure, again, see if you should be using solid or dotted line. And then also remember you need to shade. And you're going to figure out your shading by testing a point. So try that one out for tomorrow. All right, now you may also get some problems that are word problems that involve inequalities. Let's look at number 3. It says Manny has $15 to spend at the fair, costs him $5 for admission, 75 cents for each ride ticket, and 25 cents for each game ticket. Write an inequality for the number of ride and game tickets he can buy. All right, remember on these word problems, sometimes it's a good idea to go through, circle the information that's important here. To try to do it. So we have $15, $5, 75 cents, 25 cents. So we want to come up with some kind of inequality here to describe this one. We know his total is $15, so that's going to go on one side. Now everything else that he spends in this case should be less than or equal to that. Manny can't spend more than what he has. So now we need to figure out, well, what's going to go over here? Okay, well, it costs him $5 to get in. He's going to have to pay that no matter what. Plus 75 cents for each ride. Okay, now we don't know how many rides he's going on, so this is where you'd pick a variable. Let's use R for rides. Plus, he may play some games. Those are 25 cents each. So 25 cents for each game. And let's use G for games. So now we have an equation here that we can solve. Let's take it one step farther, though. Let's simplify this a little bit. Let's get all our money together here. So we know after Manny has paid that $5 to get in, what he's going to have left here is $10, basically, to spend on both rides and games. So here's what we want to be using for the rest of these questions. All right, so for the first question, it says if he buys 10 game tickets, how many ride tickets will he be able to buy? Well, we should be able to find that out. If we plug in 10 for the game tickets, substitute that in, it shouldn't be too hard to solve for how many ride tickets. So by doing a little substitution here, if we multiply 25 cents times 10, that gives us $2.50. Subtract that from the $10 he has left, and that leaves $7.50 for rides. Divide by 75 cents, and we find out that he can ride on 10 or less games. Or he can do 10 or less rides. All right. For the next question, using the same equation here, what's the maximum number of ride tickets he can buy? Well, if he's going to do the maximum number of rides, I think we can assume that he would play 0 games. So what you'd want to do on this one is same equation, except this time, instead of plugging in 10 for the games, let's say he does none. That means all his money is going to be spent on the rides. So anything times 0 is 0. What we have now is that he has $10. Games are 75 cents each. Doing a little dividing, we find, sorry, here, wrong variable. We find that his rides have to be less than or equal to, and this one doesn't come out to be nice. You get like 13.3 repeating if you divide that out. Well, what does that mean then? Can he go on 14? No, 14 would not be less than 13.3. The maximum he can go on would then be 13 rides, because we have to stay less than or equal to that. So that would be the answer for that one. For tomorrow, I want you to see if you can answer this last question then. What's the maximum number of games that he could play? All right, flipping to the back. We're also going to look at some other types of graphs. We looked at absolute value graph from yesterday. Recall that absolute value graph. When you graph that one out, if you just graph out y equals absolute value of x, that was that V-shaped graph that hit at the origin. Okay, so what we can do is, if there's some other numbers associated with the absolute value graph, we can use those to help us quickly figure out where the vertex of this is. The vertex of the absolute value graph is kind of the point. This point right here is called the vertex. Right now it's at 0, 0 when you graph y equals the absolute value of x. These numbers, if we're looking at this next equation we're going to be doing, these other two numbers, 5 and 7, shift our graph. Okay, so they'll shift the vertex of the graph. Let's read through and how it does it. If you have any number outside the absolute value added or subtracted, that moves the vertex up and down. So this 7 is going to move our absolute value graph up or down. If it's positive, it moves it up. If it's negative, it moves it down. So this 7 is going to move it up 7. So the vertex, we know the vertex now, if it moves up 7 from 0, will be at 7. The 5 is also going to move it, the plus 5 in here. Now, normally plus 5, well, first off, anything inside is going to move it left or right. Inside there, that plus 5, normally what we'd think plus 5 would move to the right, but inside a function is always opposite. So anytime you're doing some type of number or multiplying or adding inside the function, it's always opposite what you would normally do. So plus 5 normally would move it to the right. Here it's going to move it left 5. Okay, if we move left 5, that means from 0, our vertex would be at negative 5. So to kind of recap this, anything inside the function is going to move left or right, and it's always opposite what we'd normally do. Outside the function is going to move it up or down, and it's just, and outside you just do what you'd normally do. Plus and minus would be always what you normally do. So let's see if we can use that to help us quickly graph one of these absolute value functions. Number 4 wants us to graph this. We want to figure out, okay, what are these two numbers doing? Minus 2 is outside. Outside we know is up or down, and it's just what you'd normally do. So this would move it from 0, 0 down 2. All right, inside we have a plus 1. That's going to move it left or right. Inside a function is always opposite. So normally plus 1 would move to the right, but it's opposite, so this would shift it left 1 space. So if we start at 0, 0 and go left 1, down 2, here's our new vertex. Now we just have to draw out the rest of the absolute value graph. And the rest of the absolute value graph on each side is a slope of 1 or negative 1. So on this side we go up 1, right 1, up 1, right 1, up 1, right 1, and we can get the points here. On the other side, the slope is up 1, left 1, up 1, left 1, up 1, left 1. So that's that side. Connecting them now, we would have the graph. Okay, for tomorrow, the last one I want you to try, see if you can try out number 5 and graph that one. And we'll finish the notes tomorrow.